You know that the area of this circle is pi times the radius squared. But why is the formula pi r squared? And how could you prove it? Well, by the end of the programme, you'll have a way of doing it. Let's start by reminding ourselves what pi is. It's been known for thousands of years that the ratio between the circumference of a circle and its diameter is a constant. And that's the constant pi in the formula for the area. But how would you find the area? And are there any ways we can save ourselves some work? Well, one way is to use symmetry. Using a quarter of the circle makes the calculation easier. And then to get the area we want, we only have to multiply by 4 at the end. We want to find an area, and you've already used the idea of integration to find areas. So what integral would it be for the quarter circle? To set up the integral, you approximate the area as we've done here by a series of rectangles, either the blue ones, which fit inside the circle, the lower sum, or we can use the red rectangles, which enclose the circle, the upper sum. Next, you write down the area of each rectangle. That's the function value times the width, and form the upper or the lower sum. In either case, by taking narrower and narrower rectangles, the limit of the sums gives us the integral between these endpoints. So for our quarter circle, the value of the integral will be the area we want. Now it's easy enough to work out a numerical value for the area. But that still doesn't give us the formula pi r squared. What we're after is something we can apply to all circles. And to get that, we need a way of calculating integrals which doesn't involve working out limits of sums. And that's what this programme's about. A method of evaluating integrals without finding the limit of sums. You'll be able to use this method for lots of integrals. So let's leave the circle for the moment and start by looking at an easier problem, although at first sight it may not look like it. You'll recognise this curve as the cosine curve. And here's the sine curve. You'll see how that fits in later. But for the moment, I'm interested in the cosine curve and this area here between 0 and pi over 2. How would you find it? Well, this lower sum approximates the integral of cos from 0 to pi over 2. You could work it out, but there's a lot of calculation. And to save all that effort, we've used a microcomputer.
This micro is programmed to evaluate integrals of the cosine function for us as the limit of lower sums. And at the moment, I've got it set up to find the integral of cos starting from 0 and going up to a. That's this integral. Now, Anne wanted the integral from 0 to pi over 2. So to start with, let's look at that. Here's the picture Anne had, and it gives a lower sum approximation of 0.8141. If we decrease the width of the rectangles, the lower sum approximation goes up to 0.9237. Decreasing the width again gives us 0.9761. And if this process is repeated until two successive approximations agree to, say, 4 decimal places, we get the limit of the lower sums. And that turns out to be 1. So the integral of cos from 0 to pi over 2 is 1. And that means this area is 1. Now what we're interested in is finding a pattern. So let's have a look at some more integrals. The micro will find the integral of cos from 0 up to any value of the right-hand endpoint a. What it does is calculate the lower sums and then take the limit. So how about the integral from 0 to pi over 3? This time the answer is 0.8661. That's less than the 1 I got for the integral up to pi over 2. And that's what we'd have expected. It's just this area, and I can see that it's less than this one. So choosing the right-hand endpoint of the integral as a number between 0 and pi over 2 gives us the corresponding area. But what happens if the right-hand endpoint is further away, say at pi? Well, this time the integral is 0. That may have surprised you, but remember, integrals aren't the same as areas. When we calculated these integrals, we took the limit of lower sums, and each sum is made up of terms which are function value times subinterval width. Now here, cos is positive. All the values in the sum are positive, and so the integral itself is positive. Whereas here, each value of cos is negative. So the contributions of function value times subinterval width must also be negative. And because of the symmetry of this curve, in the limit, the contribution to the integral from this bit has to be minus the contribution from this bit. They cancel each other out, and the result is 0. So what happens if we move a along to 3 pi over 2? What would you expect that integral to be? Let's use the symmetry again. Cos is above the axis here, so this bit contributes plus 1. Here, cos is below the axis, and this area is twice the size of that one. So the contribution from here will be minus 2. And 1 minus 2 gives minus 1. And the micro agrees. So now you can probably predict what the integral from 0 to 2 pi will be. As you'd expect, it's 0 again, because the positive contributions cancel out the negative one. I've recorded all these results in a table, so let's take a closer look at it. Here we've got some values of a, with corresponding values for the integral of cos from 0 to a. It looks as if this is a function, and indeed it is. It comes from taking the integral from 0, so I'll call it I. So we've got I of a equals the integral of cos from 0 to a, and I is the integral from 0 function. Well, one of the first things I'd like to do is to see what the function looks like. So I'll get the micro to plot these points for us. The integral from 0 to pi over 3 was about 0.87, and the micro will plot that for us on the axes above. Up to pi on 2, the area was 1, which is a bit bigger than 0.87, so that'll give a point higher than the first one. When x equals pi, we found that the positive and negative contributions cancelled out. The integral was 0, that gives a point on the x-axis. At x equals 3 pi on 2, we got a negative value, so that gets plotted below the axis. At x equals 2 pi, the value was 0 again. And finally, we put in the value at the right-hand edge of the screen. Well, are there enough points there for you to be able to draw a graph through them? We don't really have enough information to do it yet, so let's get the micro to fill in the gaps. To start with, contributions to the integral are positive, so the integral from 0 function increases. After x gets through pi over 2, negative contributions are being added, so the integral function decreases, passing through 0 and becoming negative. That continues until x reaches 3 pi over 2. After that, positive contributions are being added, and the integral function increases once more. And that looks familiar. I expect you recognize it as the sine curve. So it looks as though our integral from 0 function is given by I of a equals sine a.
So, for the cosine curve, we found that if we keep the left-hand end fixed at 0 and vary the other end, we get the integral from 0 function I, which looks the same as the sine curve. But what happens if we choose the left-hand end to be different from 0? Let's see what happens if it's pi over 3, and work out the integral from pi over 3 to pi over 2.
Well, I can get the micro to find that area in the usual way. The answer is 0.1339. but that's just this much, the bit from 0 to pi over 2, minus this much, the bit from 0 to pi over 3. So the integral of cos from pi over 3 to pi over 2 is equal to the integral from 0 to pi over 2 minus the integral from 0 to pi over 3. And you've seen this sort of thing before. We even had a notation for it. It's this. Where I is the integral from 0 function. You may remember using this notation for x to the 5th. You had this. The integral of x to the 5th dx equals x to the 6th over 6 from a to b. Here, the integral from 0 function is x to the 6th over 6. And the important thing to notice is that x to the 6th over 6 is a primitive of x to the 5th, which just means that the derivative of x to the 6th over 6 is x to the 5th. And here, our integral from 0 function is sine, and again, the derivative of sine is cos. So in each case, the integral from 0 function of a function f is the primitive of the function we started with. Is this a general pattern?
Well, let's use those two special cases to make a conjecture. And it's this. If I is the integral from 0 function, two things are true, and this is the easy one. This is the integral from 0 to b, and subtract 0 to a. And you get the integral from a to b. And the second thing, which isn't obvious, is that I is a primitive of f. So what we've got is this conjecture, and we need to show that if we differentiate the integral from 0 function I, we get back to our original function f.
Well, here's a graph of a function f. Just as for the cos function, we've got the integral from 0 function I, which is I of a equals the integral of f from 0 to a. And that corresponds to finding this. Now, what we'd like to prove is that I prime of a is equal to f of a. So we need to look at the definition of I prime of a. Here it is. It's a limit, as h tends to 0, of the function value at a plus h minus the function value at a divided by h. Let's interpret that derivative on the diagram. I of a plus h is the integral up to here. Now we want to take away I of a, which leaves us with this, which is the integral from a to a plus h. So what we want to show is that as this width gets narrower, this integral divided by h converges to f of a. We want to investigate this shaded bit. That's I of a plus h minus I of a. Now, the smallest lowest sum we could get would be where there was only one subinterval, giving this rectangle of width h and height little m the smallest value of f in this interval. So little mh must be less than or equal to our integral expression. And in the same way, the largest upper sum is given by this rectangle, again of width little h, but height big M, the largest value of f in the interval. So our integral expression is less than or equal to big M h. But we want the limit of this divided by h to get I prime of a. So I divide by h. And now all we have to do is take the limit. the limit of this middle bit is I prime of A. What about the other terms? Well, as little h tends to 0, both little m and big M tend towards f of A. So I can write f of A for the limit of both of them. So now I prime of A is sandwiched between f of A and f of A. And the only way that can happen is if I prime of A is equal to f of A. So the derivative of I is equal to f, as we wanted.
So our integral from 0 function I is a primitive of f. And that's true for any function f. What's more, the integral of f from a to b is I of b minus I of a. But remember that a function has more than one primitive. Would this work for any primitive? In other words, if I replaced I with any primitive of f, would this still be true?
Let's suppose I is our integral from 0 function. We know it's a primitive of f, so I prime equals f. Now let's choose any other primitive, big F. Again, being a primitive means big F prime equals little f. Now these two expressions mean that I prime and f prime are equal. In other words, I prime minus big F prime equals 0. And that's the same as saying that the derivative of I minus f is equal to 0. Now what functions have 0 derivatives? The only possibility is a constant function. So I minus f is a constant. In other words, I equals f plus a constant. But what we're really interested in is whether this function, big F, can be used instead of I to work out integrals. What happens if we try to find the integral of f between a and b in terms of big F? Well, we've already got this from the definition of I. And I is equal to f plus c, so if we substitute for I, we get this, f plus c minus f plus c. And then if we get rid of the brackets, the c's will cancel, and we're left with f of b minus f at a.
So what that means is that we can replace I by any primitive of f. What we've got is this, that if big F is any primitive of little f, then the integral of f from a to b is given by this. And that's the major breakthrough. It's so important that it's called the fundamental theorem of calculus. Now, let's see what that means for our cosine function. It means that here we don't need to worry about these rectangles anymore. We can go straight to this expression for the integral. All we need to do is to choose a primitive of cos. And the most obvious primitive to choose is the sine. So the fundamental theorem tells us that to find an integral, we need only search for a primitive. The next question is, how do we go about finding one? Well, the derivative of big F is the original function little f. And you've already seen a table of derivatives in Unit 2. Here it is. Here's x to the n, with its derivative n x to the n minus 1, and sine with its derivative cos. Now, to find primitives, all we have to do is to read the table the other way around. So here's cos with its primitive sine, and a primitive of sec squared is tan. So provided we want to integrate one of these functions on the right-hand side, we can look up its primitive on the left-hand side of the table. Now, remember, we began the programme with the problem of proving that a circle has area pi r squared. How can the fundamental theorem help us with that? Mike?
First of all, I'm going to find the area of a circle with radius 1. So what I want to do is prove that the area of such a circle is pi. And as Anne said earlier, it's easier to work with a quarter circle. That's what I've got here. I'm interested in this area. And if I think of this curve as the graph of a function f, that means the area is given by the integral of f from 0 to 1. So the next thing to do is find the rule for f. Let's take a typical point on the circle and draw in a perpendicular. This distance is x, and this is 1, the radius of the circle. So by Pythagoras, this distance must be the square root of 1 minus x squared, which means that f of x is root 1 minus x squared. So what we want is the integral between 0 and 1 of root 1 minus x squared dx. And this is where the fundamental theorem comes in. It tells me that in order to work out such an integral, all I have to do is find a primitive, big F, of my function. And once I've done that, my integral will be equal to big F of 1 minus big F of 0.
Before the programme, we asked you to differentiate this rather nasty-looking function, which turned out to have derivative the square root of 1 minus x squared. So, reading the table from right to left, Mike needs to use this function as his primitive.
So here's big F. If I put x equal to 1 in here, this term disappears, and I'm left with a half arcsine 1, which is a half times pi over 2, which is pi over 4. And putting in 0, both these terms disappear, so f of 0 is 0. That means that f of 1 minus f of 0 is pi over 4. So the area of my quarter circle is pi over 4. And so the area of a complete circle is pi. And for a circle of radius r, scaling by a factor r in both x and y directions gives the area as pi r squared.
Well, you've just seen how to evaluate an integral using the fundamental theorem of calculus. And the fundamental theorem tells you that you don't have to take the limit of sums every time you want to evaluate an integral. All you have to do is to find a primitive. But finding primitives isn't quite as straightforward as finding derivatives. There are, however, standard techniques, and we'll discuss these in the rest of this block. In this programme, we used integration to find areas, but in the next programme, we'll use integration to find volumes. Have you ever wondered how you'd calculate the volume of a sphere, like this?